on artificial neural networks. And it's just fascinating to go through this, but microscopes became good enough to see individual neurons around 1905. The first drawings of neurons shook the neuroscience world and led the pioneers to a Nobel Prize. With neurons being the fundamental unit of information processing in the body, AI researchers attempted to create a model of a neuron and neural networks. The first neuron model of the perceptron was formally defined in the 1950s. We believed the neuron received a chemical and electrical input from other neurons, processed the information in the neuron cell body, the soma, then decided to fire or not fire, sending the process signal to the next neuron. The incoming information is represented as X, or you can think of an individual pixel in an image. There's a set of weights, W, equal to the number of inputs, which the inputs are multiplied by. There's an added bias, B, which is sometimes necessary to properly solve a problem. So we can define a perceptron as the function f of x is equal to 1 if x times w plus b is greater than 0, or f of x equals 0 if x times w plus b is less than or equal to 0. So again, a little mathy here, but basically it's less than, greater than, depending on your results. But notice how it's not much more complicated than when we say f of x is equal to x times w plus b. It's similar to the equation of a line, y equals mx plus b, in slope-intercept form. Y is the output, m is the slope or the gradient of the line, x is the input, and b is the y-intercept. So the value of y when x is equal to 0. But let's look at an example of using neural networks. The example of identifying cats and dogs. So children struggle at first. They identify dogs, see a cat, and they say dog. And when they're correct, and when they're not, we say no, that's a cat, so that they learn the difference between the two. Deciding between two categories like cats and dogs can be thought of as drawing a line. We can graph the examples we see, say by size and some value of domestication, and learn a line which separates the two categories correctly. With each new example, the line can change to correctly classify. So you might want to pause this video. You can check this out. You can visualize and play with all kinds of neural networks on the TensorFlow playground. And a lot of these graphs come from there, but you don't need a lot of like math or even coding. It's a lot of like clicking, and you can kind of get a sense for how these things work. And it's very cool to see. But here's a graph of data we want to classify shown by the colors orange and blue. And we can think of these as cats and dogs as well. But just ask yourself, can you draw a single line to separate the data points into their respective classes? We want a neuron to learn the line. So we can have like x1 and x2 as input. It goes to a single neuron, and that neuron is like the cell body, and the outgoing line is like the axon. So after some training, the neuron learns a line. And you can see the decision boundary by the white line bisecting the data. So yeah, here are the results, and we can see that line separating the two classes, and it's just everything on one side is blue and everything on one side is orange. So the problem can be defined as find the w and b, which gives f of x returns blue if w times x plus b is greater than some threshold, and it returns orange if it's less than some threshold. Notice how the neuron changes its line once trained. The lines leading to and from the neuron represent the weighted connections. So you can see how thick it is. And finding a decision boundary is, I believe, the essence of intelligence. Here's what I believe to be the essence of intelligence. It's finding a decision boundary. Making a decision based on a gradient between two things, yes, no, true, false, move or don't move, etc. The perceptron stops learning when it finds an appropriate line to separate the two classes. Pause to consider that there are an infinite number of lines we can find to separate this data. If the data is not linearly separable, then the perceptron will continue to struggle and fail to find the decision boundary. So here's another example of data. And it would be really hard, I would say, to find an equation that's linearly separable. You could see, can you draw a straight line to separate the two classes? It's not really possible. And if we use that same neuron architecture in our simple model, it finds some line, but it hits an unsurpassable limit. It can only be so accurate. I do want to talk a little bit more about neural networks and the more complicated problems. So eventually we're going to build up to the XOR problem, which is the exclusive OR operation. But we'll build up to that first by trying to understand the AND operator. So when I say like x1 and x2, and basically, we have that input x, which is x1 and x2, and we have w, which is the weight 1, weight 2, and it can either be true and false, so we're just simplifying that, or 1 and 0. And the logical AND operator in a truth table, when we have x1 and x2, we lay out all the possibilities. So we say, true and true, true and false, false and true, false, false. And basically, it makes sense, right? Like in English, that when we have x1 and x2, it's only true with the AND operator when we get the x1 and the x2 both true. But we can graph that on a line, and we can have the y-axis as x2 and the x-axis as x1, and we start to see this little graph of possible points. So can we draw a line to separate x1 and x2? So it returns true and false properly. And yes, we can, right? We can draw a bunch of lines. And basically, we draw a line so that the upper right square here, the 0.11, so which is true, we can draw a line across that square basically, and anything above it is true, and anything below it is false. And that meets our conditions. And again, we can draw a lot of lines actually to make that separation. And if we look at the logical OR operator, so that's basically the only time it's false is when both things are false. And again, looking at a graph here, can we draw another line to separate them? And just like the AND, we can find a line. We just have to move the line and say everything above it is true and everything below it's false. But there is a tricky problem with the XOR problem. The XOR problem is exclusive, so it's weird. So you can only have one or the other. A lot of times that's how we think of it in English too. Only x1 or x2 can be true, and the other has to be false. So again, you can see the truth table here. We also have that same graph, and we see what's true and what's false. And can we draw a single line to separate the two classes? Although XOR doesn't seem so different from AND/OR, it's surprisingly more computationally complex. We need two lines, or at least two neurons, to define the decision boundary. Once we can draw two lines like so, then we can actually separate the classes. So here's an example of the neural network for AND/OR. We have the input layer and the hidden neuron with the output, but the XOR function can logically be written in terms of AND, OR, and NOT. The NOT function is just what it sounds like. Not true is false and not false is true. So we can rewrite the XOR function as x1 or x2 and not x1 and x2. You can spend some time if you want trying to find the proof for this, or you can just believe me. But the interesting thing here is that we have to change the number of hidden neurons in the hidden layer to make this problem function. This is why there's like computational limits to how neurons can process information. There are very strong proven limits to just the perceptron, but when we start to add neurons together, some interesting things happen. Another way to think about this though is imagine the graph for XOR is a square piece of paper. How can we use a single line to separate the two classes? So maybe we can do it with a single line. And what we can do though is with a piece of paper, you can fold two corners up, the ones that are true. And now what we can do is draw a line in this three-dimensional way, one single line to cut through them. Okay, so this was a lot, but here's the key takeaways. The hidden layer of neurons, of which there can be many, learn a representation of the data that allows for better decisions. We can visualize it as emphasizing or diminishing the input, which creates an altered topology, like flexing or folding a piece of paper or cloth to draw a decision boundary. This extends to multiple dimensions. So instead of decision lines, we can have a decision plane. By mathematical proof, neural networks are universal approximators of continuous functions. Anything which can be represented by a continuous function can be learned by a neural network. You could potentially learn any function with enough neurons needed in a single hidden layer. So you could just have one layer. But it's also proven for multiple hidden layers, where each layer is learning from a slightly modified previous layer. And that's the big secret of deep learning, is basically you're stacking hidden layers. One neuron goes into another, one neuron goes into another for however many times. So we can see that the universality, the generalizability of neural networks, but this is all based on the most simple model of neurons. We are still only considering neural architectures which feed forward, then send an error signal back. Real neurons are humming with information and have all kinds of connections. The model we had, which is of the input x1, x2, etc., sending a signal of on or off, relates to the synaptic connections between biological neurons. We thought of synaptic connections as sending a charge, like a metal transistor wire carries electricity. But research has shown human dendritic connections can solve the XOR problem. So looking closely, the dendrites generated local spikes, had their own nonlinear input-output curves, and had their own activation thresholds, distinct from those of the neuron as a whole. The dendrites themselves would act as AND gates, or as a host of other computing devices. This is from Quanta Magazine. So the closer we look, the more computational complexity we find. So again, we saw that the XOR problem was really difficult and required more complex computation. But when we looked at the actual biological neurons, what we thought were simple synapses carrying a charge, like electricity in a wire, it's kind of like if you looked at your transistor and there was a whole other computer inside your transistor. So the computation that our brains, the human brain specifically is doing is just like mind-blowing, and we're still learning about these things. This was huge in the field when I was coming up. When a model is too simple for the data, it has high bias and low variance. The line the model draws is too rigid. When a model overfits past data, it can be too complex for the problem. So it has low bias and high variance, a line that has high or low squiggles. An overfitting model has a high degree polynomial function, which makes it easy for the function to go wildly high or low in estimates. An overfit model can perfectly fit past data, but fails on unseen data because its estimate is too far off. Ideally, the model will find the optimal function for the problem, the lowest degree polynomial function necessary to predict the true data distribution from past and future events. So that's like Occam's razor. You want to have a more simple hypothesis. Gosh, I hope this isn't too complicated, and I don't want you to be too worried, but the main thing is just that our brains are incredible. The way neural networks can be organized is fascinating, and it's enough to study for a lifetime. It's so interesting. And all of our, apparently, thoughts, feelings, emotions, it stems so much from these function of neurons. But given the high dimension... Thanks for watching. If you enjoyed this clip, please consider checking out the full video and the series linked in the description.